Alright, we're going to continue with section 14.6 in this video, and we're going to talk about now how to convert between spherical and rectangular coordinates. So to convert, the spherical coordinate rho phi theta to the rectangular coordinate xyz, we use x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, z is equal to rho cosine phi, and then also you may end up using, let's say, where that rho sine phi is equal to the square root of x squared plus y squared. So if you're given rho phi and theta, you can use these equations to find x, y, and z. So on the other hand, to convert the rectangular coordinate x, y, z to the spherical coordinate rho, careful not to confuse your order, rho phi theta, we use rho squared equals x squared plus y squared plus z squared, and then tangent of phi equals the square root of x squared plus y squared over z, and tangent of theta equals y over x. So you're given x, y, and z. You need to find rho phi and theta. You would use these equations to do that. All right, so now let's talk about the key point of this lesson, which is how to set up a triple integral in spherical coordinates. All right, so first we want to talk about what is our region D. How do we write that in spherical coordinates? So let D be equal to the set of points rho phi theta, such that theta varies between some alpha and beta, because remember, theta doesn't always have to go between 0 and 2 pi. It could go between whatever, say pi over 4 and 3 pi over 4, for instance. So that's why we don't use 0 and 2 pi here. And then our phi goes from function of one variable h1 of theta to function of one variable h2 of theta. And then our rho goes from function of two variables to function of two variables. So it goes from f1 of, let's see, I'm trying to decide if we should use theta phi or phi theta. It really shouldn't matter, but I want to stay in line with what your textbook does. Yeah, we're going to maintain the order from the points, which is phi theta. So rho varies between f1 of phi theta and f2 of phi theta. Sorry, I can barely fit this on the page. All right, so that's what our region D, how we write our region D when we're working with spherical coordinates. But now we need to talk about the restrictions on the different things that we have here. So this is where beta minus alpha has to be between 0 and 2 pi, which will ensure that our theta is between 0 and 2 pi. Remember, phi has to always be greater than or equal to 0 and less than or equal to pi, which means this has to be greater than or equal to 0 and this has to be less than or equal to pi. So h1 of theta is greater than or equal to 0 and less than or equal to h2 of theta, but h2 of theta has to be less than or equal to pi. And then our rho has to be greater than or equal to 0, which means this thing has to be greater than or equal to 0. So, and f sub 1 of phi theta is greater than or equal to 0. So that ensures that we maintain our restrictions on rho, phi, and theta. So now that we have that, we can actually go ahead and set up the triple integral. So if f is continuous on D, then the triple integral over D of f of x, y, z, dv equals the iterated integral so alpha to beta h sub 1 of theta to h sub 2 of theta then f sub 1 of phi theta to f sub 2 of phi theta. And now we need to rewrite our integrand, but we have to change from x, y, and z to spherical coordinates. So this is going to take up a good amount of space. So you want to try to get this as close to your integral as possible. So f of our x, which was rho sine phi cosine theta, then our y, which is rho sine phi, sine theta, theta. And then our z, which is rho cosine phi. And whenever we integrate in spherical coordinates, similar to what we had in polar coordinates and cylindrical coordinates, we're going to have this factor out here. The factor this time is not r, it is rho squared sine phi. So that is part of the integrand always whenever you're doing an integral in spherical coordinates. All right, now these are rhos, so this is d rho. These are phis, so d phi. And these are thetas, so d theta. All right, so that's how we would set up a triple integral in spherical coordinates. So now let's actually go through and we'll do an example. So we're going to look at number 10 on page 951 in your textbook. So page 951, number 10. So when you do a triple integral in spherical coordinates, now in the past we've sketched the two-dimensional region in the XY plane. Like if we projected our three-dimensional region down into the XY plane, you rarely need to do that for spherical coordinates. Sometimes you might have to sketch your three-dimensional region, but oftentimes you won't even have to do that. So number 10 says the triple integral over d of x squared plus y squared plus z squared quantity squared, where d is the solid region bounded above by the sphere x squared plus y squared plus z squared equals 1, and below by the upper nape of the cone z squared equals x squared plus y squared. So, and remember this is to get our bounds. We're told that the top is x squared plus y squared plus z squared equals 1. The bottom we were told was the upper nape of the cone. So they gave us z squared equals x squared plus y squared. But they told us that it's just the upper nape of the cone. So that actually for us, it was just going to be z equals the square root of x squared plus y squared. That's the upper nape of the cone. All right, so now we want to take this that we have and we're going to convert all of this into spherical coordinates so we can set up our integral. All right, so first here, we know that x squared plus y squared plus z squared, that's the same as rho squared. So now we're using those conversions that we have to convert from polar to rectangular or spherical to rectangular or rectangular to spherical. So that's equal to 1, which says rho will be equal to plus or minus 1, but we know rho has to be greater than or equal to 0, so we get rho equals 1 there. And here, if we substitute everything that we know in, z is the same as rho cosine phi. And the square root of x squared plus y squared is rho sine phi. All right, so and make sure we do our algebra correctly here, otherwise we'll lose some pertinent information. So we want to move everything over to the left. We can't immediately go and divide by rho because rho could be 0. So we have to, the way we account for that is move everything over to one side. So rho cosine phi minus rho sine phi equals 0. Then we factor out a rho. We get rho times the quantity cosine phi minus sine phi equals 0, which tells us rho equals 0 or cosine phi equals sine phi. And the cosine phi equals sine phi tells us that phi will be equal to pi over 4. So now, remember we just need rho phi theta. There's no restrictions from what we have here. Now you could, actually let me sketch this in 3 dimensions and then I'll talk about what you could do if you wanted to go into more detail for theta, but it's not necessary though. And you'll see that easier from the sketch. So we sketch. So this is like the ice cream cone problem that we've seen in previous sections. So we have the upper nape of the cone and we have the sphere. So rho goes from the smallest our radius is from or distance from the origin is 0, and it goes all the way out to 1. And because we're on the sphere, at the longest point at all times, we know our 1 is right there. We don't have to worry about, like, say for instance, this being something other than 1 because we're on the sphere. So it goes from 0 out to whatever, 1/2, 3/4, all the way out to 1. So our rho is going to vary from 0 to 1. Our phi this phi equals pi over 4, that's what we got from the cone right there. So that tells us that our phi is going from here, phi is 0, and we're on the z-axis, and it varies out to the cone, which that cone is pi, the phi equals pi over 4. So we can see what our phi varies between 0 and pi over 4. I mean, we would have to solve for that, but we can see that our lower bound for phi is 0. And then just from the nature of the picture, we can tell that our theta goes from 0 to 2 pi. So rho goes from 0 to 1, phi goes from 0 to pi over 4, and theta goes from 0 to 2 pi. Now, if you wanted to, you could project or look at the intersection of the top with the bottom to get that circle right there, the circle where the cone intersects the sphere, and then look at that to use to find out your theta. But you all are very familiar with circles, so you wouldn't have to go through that algebra to try to figure that out. You would just end up getting this circle right here and to try to figure out what your theta is. So our rho varies from, what did I say, 0 to 1. Our phi varies from 0 out to pi over 4. And our theta varies from 0 to 2 pi. And now we can go ahead and set up our integral. For sake of time, I'm not going to write down d. We have everything we need right there, so I don't need to write it in that set notation. So now we have the iterated integral. Our theta went from 0 to 2 pi. Our phi went from 0 to pi over 4. And our rho went from 0 to 1. Our integrand we were given in the problem was x squared plus y squared plus z squared, quantity squared. But remember, we need to convert to spherical coordinates. X squared plus y squared plus z squared is rho squared. So we have rho squared, squared, and then don't forget about that factor, rho squared sine phi that we're going to have there. Then these are rhos, so that's d rho. These are phi, that's d phi, and those are thetas, so that's d theta. I'm not going to integrate this, but I will show you all the technique that you can use. Now you can only do this when all of your bounds are constants, and you can split up your integrand into a product of a function of each one of these. So all your bounds have to be constants, and you have to be able to split up your integrand into a product of a function of phi times a function of, a function of rho times a function of phi times a function of theta. That's the only time you can do this. So this is equal to, and it makes integration possibly a little bit easier, depends on how you look at it. So the integral from 0 to 2 pi, those are my thetas. So I look at what I have in terms of theta in here, and it's just 1. There are no thetas in there, so that's 1 d theta. And then from 0 to pi over 4, and I look at my phis that are in here, and I can write those as a function by themselves. So that's just sine of phi, d phi. And then 0 to 1. And I look at the rows that we have in here. So we have rho to the 4th and rho squared, so we get rho to the 6th d rho. And then you can evaluate those 3 single integrals and just take their product. So remember, again, you can only do this when all of your bounds are constants. All of them have to be constants, and you have to be able to split your integrand up into a function of theta times a function of phi times a function of rho. And you can do this even with rectangular coordinates. So if you have rectangular coordinates on a triple integral, all of your bounds are constants, and you can split your integrand up into a function of x times a function of y times a function of z, then you can rewrite it this way. But please don't try to do that if all those conditions that I laid out are not met. All right, so we'll stop this video here, and then I'll do a couple more 14.6 examples in the next video.